following presentation will cover some of the challenging freezing drizzle patterns within the 15th OWS AOR. In this presentation, we will discuss a general description of freezing drizzle, contributing factors, synoptic patterns, forecast techniques, scenarios, challenges to forecasting, and some MetWatch techniques to assist in forecasting freezing drizzle. We should start with a general description of freezing drizzle as it pertains to the type that occurs when the entire atmosphere is below 0 degrees Celsius. This is also identified in the first weather group, TTP, as the supercooled warm rain process. It occurs when supercooled liquid droplets grow by collision and coalescence in a below freezing environment. If the temperature in the standard low levels, generally below 10,000 feet, remain between 0 degrees and minus 10 degrees Celsius, supercooled liquid droplets remain that way due to the lack of heterogeneous nucleation and no ice crystal development. The lack of ice crystal development chokes off any potential for snowflake development, and the liquid falls to the ground as drizzle, freezing on contact on the below 0 degrees Celsius surface. Some of the contributing factors include an environment where saturated air below 10,000 feet exists, an environment where the surface temperature is 0 degrees Celsius or colder and remains between 0 degrees and minus 10 degrees Celsius below 10,000 feet or through the saturated layer, an environment where rapid drying, possibly a subsidence inversion, occurs immediately above the saturated layer, some type of mesoscale lifting mechanism, such as low-level convergence, cyclonic circulation, upslope, or frontal lift. Let's take a look at what type of synoptic situations will provide these types of environments. There are many synoptic patterns where freezing drizzle can occur, but we will focus on two that occur in the 15th OWS AOR and are the most challenging: post-cold frontal synoptic patterns and the backside of an occlusion or deformation zone. With the post-cold frontal pattern, the cold front passes the station, and as the upper level troughs also pass, the mid and upper levels dry out rapidly, leaving only the low level clouds wrapped in the low level cyclonic circulation behind the front. If the low levels are completely saturated, drizzle will occur as supercooled liquid droplets begin to fall and freeze on contact. This typically occurs where the snow transitions behind the cold front. The second type we will discuss is the backside of an occlusion, or the extreme back edge of the deformation zone snow. As the mid and upper levels begin to dry out with the passage of the upper level low clouds remain wrapped around the occluded low. This can provide conditions necessary for freezing drizzle. Let's take a look at some forecast techniques for freezing drizzle. We've just briefly discussed one, which would be recognizing the pattern where the freezing drizzle might occur. The challenge is most systems go through this exact development process, but freezing drizzle is not that common. It's all about recognizing the synoptic pattern and then recognizing the typical freezing drizzle skew-T sounding, which shows up a completely saturated low level with rapid drying above. Some of the newer freezing precipitation products available, like the model precipitation type or the AFWeb's Ensemble freezing preset product, can provide a first look assistance as to where freezing drizzle may occur. Some other products that can assist are discussions done by the National Weather Service. Specifically, the area forecast discussions really get into the weeds on specific weather and what's causing it. It is a meteorological discussion and provides an abundance of information. Hazardous weather outlooks and winter storm warnings can also provide a generic overall picture of expected severe weather, including types of precipitation and travel restrictions. From the main National Weather Service map page, just select the area of interest and drill down until you see the hazardous weather conditions area. Then select the product you want to look at. As you can see, the area forecast discussion gets very specific and uses meteorological terms to describe in detail what is forecast and why. Many times the National Weather Service is already looking at freezing drizzle potential in areas you may not have considered. Of course, we always want to use our freezing drizzle TTP and run the checklist for areas of concern. Although originally developed for freezing rain, it has a freezing drizzle option built in if there are no warm layers available and conditions are right for freezing drizzle. If conditions are right, the checklist will lead you to forecast freezing precipitation under supercooled warm rain process. Let's take a look at our first scenario, which would be a post-cold frontal type. As a cold front drops out of Canada and passes Bismarck, North Dakota, the 500 millibar trough passes the station and low-level clouds and moisture remain. While there are some signs for freezing drizzle, there are also some items that don't seem to support it. Let's take a better look at the situation. The front moves past Bismarck, North Dakota near 00Z on 11 November and has moved well south by 12Z and remains there. The Galwin 500 millibar height and relative humidity chart indicates the shortwave trough passing after 0Z, which would assist in drying out the mid-levels. Notice the 1,500 millibar thickness chart beginning to dry out after the 11th at 0Z, indicating mid-level drying. However, the 1,850 millibar thickness chart still indicates 90% relative humidity over Bismarck, indicating an abundance of low-level moisture. Although the AFWEB's threat probability product is hinting at some potential for freezing precipitation, it is more to the east in Minnesota with snow in North Dakota. The AFWEB's ensemble product is hinting at some freezing precipitation near Bismarck. The Bismarck meteogram indicates a pattern in the clouds forecasters should be familiar with, and that is the mid and upper level drying between the 10th at 12Z and the 11th at 0Z, as indicated by the yellow arrows. In a likely freezing drizzle event, the low-level saturation would continue to the surface or very close to it. In this case, the extreme low levels are not saturated. The same can be said about the skew-Ts after the 11th at 0Z. While we get a nice drying effect aloft and some saturation in the low levels, the atmosphere is never really completely saturated to the surface, which is not conducive for freezing drizzle. Notice the difference in the near-surface temperature and dew point traces versus the typical freezing drizzle sounding on the right. Although there was one report of unknown precipitation near 6Z, as indicated in red, which can be an indication of a changing precipitation type, overall this remained a snow event. In this scenario, there were just too many things to overcome. It wasn't a typical post-frontal pattern. Galwin was pretty spotty with freezing precipitation forecasts. The skew-Ts indicated only partial saturation, and near-surface layer was too dry. In our second scenario, we have a late fall system moving through the Midwest with the backside of the occlusion and deformation zone passing over southern Illinois. As the 500 millibar low passes, the mid-levels dry out, but the low-level clouds remain. This scenario has a few more pros than cons, which we will review again at the end. The synoptic situation indicates the 500 millibar low southwest of the station on the November 15 12Z forecast chart, but well east of the station by 21Z. At 500 millibars, the deformation zone begins to dry out, but you can see the 850 millibar moisture remains 90% the entire period. The same pattern is indicated on the 1,500 millibar thickness chart valid at 21Z, which indicates 70% relative humidity and drying just to the east, but the 16th 0Z 1,850 millibar indicates The back edge of 90% relative humidity still over the station. Indications of mid-level drying, but low-level moisture remaining. The actual analysis charts at 500 millibars shows the low at 12Z just southwest and 00Z well east of the location. Although the surface chart does not have an occlusion drawn, moisture patterns and the upper level low supports the existence of that surface occlusion. The AFWEB's threat probability indicates freezing precipitation, although most of that is freezing rain along the occlusion to the east. The AFWEB's ensembles both pick up freezing precipitation as well. The GALWIM precipitation type chart indicates a rain-snow mix, changing to snow and then a thin band of freezing precip on the very back edge of the deformation zone. The Red Hills MOA mediogram indicates good drying in the mid-levels, with good saturation in the low levels all the way to the surface until around 18Z, then some drying in the low levels near the surface after 18Z. The SKUTs indicate mid-level drying, and between 15 and 21Z soundings, it appears to be saturated to the surface, although the surface temperature is really close to 0 degrees Celsius. It is a pretty good match to the freezing drizzle typical sounding. Although none of our observing sites carried freezing drizzle, the one with the most instances of unknown precipitation also had their freezing rain sensor operational. 2 of the 4 observation sites carried unknown precipitation as the snow was transitioning, which would have been the time freezing drizzle should have occurred. So while this was not a perfect setup, it had many of the characteristics of the synoptic pattern following an occluded low, and would have easily been a scenario where a watch would have been warranted and possibly even a warning. This scenario had a few more pros on its side, and the smaller scale tools like the SKUT and mediogram plus the ensembles indicated freezing precipitation, and temperatures in the saturated layer remained between 0 and minus 10 Celsius. As you can see, even with a better looking pattern, we still receive no freezing drizzle reports, so it is always going to be a challenge. Here are some other challenges we face as forecasters. One of our primary challenges is detection. There are known sensor issues with meteorological equipment which can report freezing precipitation when it is not occurring and also has not reported it when it is occurring. There are directions on how to handle these situations in our local procedures. Another challenge is determining if drizzle will actually occur. Just because saturation occurs in the low levels doesn't necessarily mean drizzle will occur. Conditions may look good, but then no drizzle occurs. Currently, we don't have any microscale tools to alert us to potential freezing drizzle conditions. Finally, freezing drizzle can occur anywhere the conditions are right. The synoptic patterns shown here are just 2 patterns we see frequently in the 15th OWS AOR. But freezing drizzle can occur with frontal overrunning, undercutting, and in cold air stratus with receding high pressure systems. The next few slides will show some METWatch techniques. First, we are simply going to look at radar and surface observations in AFWEBs and ADS to see if freezing drizzle is occurring upstream of your location, and if so, how long it lasted and how much fell. Are there any unknown precipitation reports in upstream observations? Determine the direction it is all moving. In these 3 examples, the freezing drizzle reports would all be moving in the direction of the yellow arrows. Behind the front, it would move in the direction of the surface cold frontal movement. In the 2 examples with the occlusion, the freezing drizzle would move with the track of the surface low pressure system. Once again, a great METWatch technique is reviewing National Weather Service bulletins and SPC mesoscale discussions. These bulletins provide specific descriptions of the event and highlight areas on maps to quickly identify the threat. SPC mesoscale discussion bulletins are written by meteorologists with many years of experience, and they explain what is happening and why it is happening. The Aircraft Meteorological Data Relay, or AMDARS, data can also be a great MetWatch tool. It provides real-time output from aircraft in an easy-to-read SKUT format, as well as text readouts. They can be very useful in ongoing VIV process and to verify how the atmosphere is changing so you can compare it to forecast soundings for accuracy. In this presentation, we covered a general description of freezing drizzle, contributing factors, synoptic patterns, forecast techniques, scenarios, challenges to forecasting, and some MetWatch techniques to assist in forecasting freezing drizzle. For more information on freezing drizzle, please refer to the references used for this presentation. This concludes the presentation on freezing drizzle.